Afternoon, everybody. Thanks for coming. We're going to talk today about the random header in the CppCon standard library. It came in with C++ 2011. It's essentially been unchanged since then. There are some things on the horizon that I will tell you about toward the end of the talk. Before I actually get into the technical details, although it's customary to give thanks at the end of a talk, I would like to ask your help in thanking somebody very important to me, someone who hardly ever gets thanked. And that would be my wife, who actually fabricated my tie that I'm wearing today. So please help me thank her. I appreciate that. Thanks very much. So we're going to talk today, as advertised, about the ideas that went into what became the random header. We'll demonstrate the most common correct usage pattern. I will show you the most common incorrect anti-pattern, and I'll explain what's wrong with it. What's really wrong with it is sociological. It's just too simple. It's too attractive. But thou shalt not do this. We will explore some toolkit designs, and you can extend that if you wish. We're going to have a little random fun. Some of this material is taken from some paper I wrote a few years ago. Those are the paper numbers are there in case you want to look them up. And there are going to be some extra slides that I've had to hide because otherwise I would go over time. But the files that I will upload will have all of the slides. So if you happen to notice that there are some gaps in slide numbering, there's some hidden slides there. So if you're interested in just a few more little details, please do download the slides or at least look at them at your convenience. So first, a little bit of background information on the general topic of randomness. Yeah, they're a pain in the butt. I said it was background information, didn't I? Okay. And of course, there's the famous statement by Don Knuth. This has been known for a very long time, and yet the temptation is almost irresistible to roll your own. Please don't do it. Please don't roll your own unless you're an expert. It is interesting that the first known algorithm for generating pseudo-random numbers dates back to around 1245. A Franciscan brother Edwin wrote about it. It was then, I believe, independently rediscovered by John von Neumann around the middle of the last century. It is considered a crude but very fast algorithm. The idea is you start with a big number, you square it, you chop off a quarter of the digits at the end, a quarter of the digits at the beginning, and what you're left is the middle of the square, and that's your next number. It's very fast. It's very crude, but it's very fast. And the failure modes are obvious. If you ever happen to get a 0, you're done, right? Okay. But nonetheless, this algorithm was in use at some point back then. In particular, it was used back then in support of what has come to be called the Monte Carlo method. It's an unusual name. It turns out it was a code name during the post-war years. Right? They were still actively involved in the Manhattan Project back then. It was developed by Ulam and actually coded on the ENIAC by John von Neumann. The process, however, known as Monte Carlo, is still in heavy, heavy, heavy use today, and it relies intimately on the generation of random numbers. The idea, of course, is that you simulate a process and then do statistical analysis on the measurements you take as a result. But nowadays, there are many more uses of random numbers. I'll just give you some highlights. There are Monte Carlo and other simulations, and yes, it's called Monte Carlo because of where the casino is. There are genetic algorithms, randomized algorithms, hashing algorithms. Not too many people I've discovered know about something called Zobrist hashing. It's interesting. It applies to board games, for example. Rearranging which most of us know better as shuffling, is a very common application of randomness. For most of us, or many of us at least, we use it to test sort algorithms, but it is used in so-called randomized tournaments, which covers everything from sporting events to the military draft. If you ever want to see some fascinating history, look at the first random draft of the US military. It's a horror story. There are jurisdictions in which the preparation of a voter ballot is randomized, so that no candidate is obviously favored by being first, for example. Random numbers are used for selection purposes, obviously in gaming. There are teachers who use it to ensure that they call on students fairly, eliminating personal bias. Don't just call on the best-looking student. Choosing performers on open mic night. For us, choosing a pivot in quicksort is often done randomly. A lot of applications in statistical sampling, in manufacturing quality control, in drug screening, auditing, trials for new medical treatments, et cetera, et cetera. It's a very long list. And one item I want to call out specifically, of course, random numbers have a role to play in cryptography. But I want to let you know at the outset that this is not a goal in the design of the random header. Cryptography has additional requirements that were not considered when this header was designed. Design goes back almost 15 years. We did not consider cryptography. So please, if you have a cryptographic application, this is not a good place to start to look. You can look at it for inspiration, but these are not the facilities you should be using, at least not without some extra work on your part. So let me start with a leading question. Suppose you have an oracle of some sort. I don't care if it's a crystal ball or if you look at some entrails or whatever you do. You have an oracle and you ask it for some random numbers, and 10 times in a row it delivers to you 0. Would you consider that random? I suspect most of us would say no. And yet, there's not enough information to answer the question. You don't have a big enough sample to know whether that's random. You just don't. Pete Becker was a well-respected member of the C++ Standards Committee. He was the project editor for C++ 11, and he's now enjoying his retirement, as am I. There's another way of expressing the same notion. This is perhaps a very well-known cartoon, but I felt it appropriate at this point. As always, Scott Adams cuts to the heart. And it turns out that getting a computer to do anything randomly is not just difficult, but astonishingly difficult. Far more difficult than most of us would like to think. It's not just hard for computers, it's also interesting. The problem is, if you look at the literature of the past 60, 70 years, as I have done, I don't claim to have read all of it, but I've read a fair amount of it. I am not exaggerating. It is littered with algorithms that were just plain wrong, but that people have been relying on. And because it's been published, people think, therefore it must be good, and some of these things are still in use today. Please don't rely on anything until it's been exhaustively tested. There are so many pitfalls. This is a very nice statement of the facts as proven by history. You don't want to write code that's embarrassingly bad. I sure don't. Here's a nice summary of the true message. And this is really at the heart of why we designed and ultimately specified the random number library in the random header. I'm essentially the principal author of the papers. If you do arbitrary stuff on random numbers, you don't get random output. You might, but you'd be lucky. And then, of course, XKCD comes along. That's what you asked for, not what you wanted. I am often asked, what was wrong with the rand function in stdlib.h, and of course, which we absorbed as cstdlib? Well, if you haven't, I encourage you to go read what the C standard says about it in C11. Here's the quote. It's a footnote. There are no guarantees about the quality of what you get. And it is known that some implementations give you not just bad, distressingly non-random bits. That's what it says. I'm quoting the standard. I did not make this up. C++ standard, C++ 17 at least, says it, I think, a little bit more genteelly. The algorithm is unspecified, which of course means unportable, unpredictable quality and performance, and oft questionable. I think that's a little gentler. But hey, it's a C function. They get to say whatever they want about it. Anyway, here is one man's opinion. I wish I knew who this was. This is what he calls himself on his blog, Indy, which I thought was kind of flattering. So whoever you are, thank you. So let's actually have a big picture look at what's in the header. This is what Bjarne comments, but he's quoting somebody else. I believe he's quoting Andrei Alexandrescu. I'm not 100% sure, but this is from Bjarne's, or was on Bjarne's homepage, or one of his homepages. What every random number library wants to be when it grows up. I love that phrase. So, at least in my opinion, there's something there for everybody. Whether you're a novice, a casual user, all the way up through expert, there's something there for everybody. So for those of us who are casual users, what you're probably most interested in is the one pre-configured engine type, and I'll make sure we all know what that means. All the words in green we will discuss. And then there are two uniform distribution class templates. They are configurable. Can't pre-configure them because we don't know your application, so you have to configure them. But for intermediate and advanced users, we have 9 more engine types, 18 more distribution templates. There's a class in case you have access to some environmental source of randomness. We'll discuss that briefly. There's a class that was supposed to help you with engine seeding. And for true experts, we have some class templates if you want to play with the template parameters. And there's actually even a function template to help authors of new distributions, in case that's your thing. So there's something there for just about everybody on the programming spectrum. Perhaps the single most important takeaway for now are the next few lines, the nomenclature that we use. It is generally not particularly well known that the traditional term random number generator actually encapsulates 2 very different kinds of algorithms. It's almost like an old-fashioned computer terminal. It had a keyboard, it had a monitor, but they were all under one dust cover. We just said it's a terminal. But you got 2 very different pieces of equipment there under one cover. Same idea here. If you talk about random number generation, there are 2 algorithms. And we need to talk about them separately, so we use nomenclature that's a little bit more precise. And if you're going to work with this, this is what you should know best. The first piece of nomenclature is the term engine. An engine is what we mean by an algorithm, or something else perhaps, that lets you obtain a sequence of unpredictable, at least ideally unpredictable, bits. In particular, uniform is the important property. And what do we mean by uniform? It's the statistician's way of saying the probability of a 0 is the same as the probability of a 1 every single time. That's the uniformity property at the bit level. okay? And the second piece of nomenclature is the idea of a distribution, which is well known to statisticians, but not necessarily to computer scientists and programmers. A distribution is a means of obtaining a variate. We think of them as random numbers. The technical term is a variate. And it's not just any variate. We want variates for our applications such that if you aggregate them and you plot them, you get a particular shape. Well, what shape do you want? I can't answer that. You have to answer that for your application. Here are some possibilities. There are lots more. It's not important that you see what these are, but just a little bit of the possible variety of what I mean by aggregated shape. The first one at the bottom left is called the normal distribution. A lot of us know it as the bell-shaped curve. But that's parameterized. How wide is it? How high is it? Where is it? Left, right, et cetera, et cetera. Okay? So these are things you will have to supply. You have to know your application well enough to decide what kind of a distribution you want. For people who are casual users, almost always what they want is a uniform distribution. If you're playing cards or you're trying to simulate rolling a fair die or something like that, what you want is a uniform distribution. If you want to roll 2 dice, you don't want a uniform distribution, unless you roll them one at a time. Okay? So you have to know what you're talking about. This is a classic example where 2 times x does not equal x plus x. Okay? So beware of even simple refactorings that seem obvious. They don't necessarily work. You have to know what you're doing. So let's talk a little bit about engines. We use the term engine both to refer to certain kinds of types and then to objects of those types. All right? So let's postulate that we have an engine object, lowercase e, whose type is capital E, and it's a function object. It's callable. It has an operator parens. Every time you call it, you're going to get some number of bits, uniformly distributed, ideally random bits. Okay? By the way, don't assume that n has to be an integer. Don't assume. It usually is, it typically is. Nothing in the definition says it has to be. Once initialized, this object has typically deterministic output, and therefore if you want to be precise, you're actually getting pseudo-random numbers. Okay? But not every engine gives you deterministic output. We have interfaces for environmental sources of randomness. So don't assume it's going to be pseudo-random. Depends on your choice of engine. Excuse me. The ideal is unpredictability. But when you have a computer, you typically have to settle for very hard to predict. That's the key. An inability to predict. That's the key. Now, there's some details, right? When you call an engine, what you get is often called a bit string in other contexts. It has a non-zero length. It's encoded as some unsigned type. There's a reason for that. Long ago, when we were designing and experimenting with this stuff, our initial idea for an engine was you make a call, you get a bit. You want another bit, you make a second call. The performance was horrible, as you can well imagine. So we said, okay, let's allow engines to give you up to 32 bits at a time. Or, back then, that was the obvious result. Okay? But we don't require anything other than there be some min and some max value, both unsigned, of course. And you can ask what those are. Min is almost always 0, but it's not required to be. Most importantly, for users, you probably don't need to know any of that. You really don't. The intent of an engine is that you get to pick which one you want. It's your choice of algorithm. You get to initialize it however you want. It's your choice. You may want reproducibility. You may want no reproducibility. It's up to you. But once you've done that, all you do is pass it around. Literally. That's almost all you ever do with it. I mean, an engine can do other things. I'll tell you about some of them later. But the single most important thing you want to do with an engine is hand it off to something else. So let's talk a little bit about distributions. The purpose of a distribution object is, again, you call it, and it gives you a result. And this is what you want. You want a variate, a random number. You do it by calling a distribution. Okay? So you have to create a distribution. Which distribution? Depends on your application. How do you create one? Depends on your choice of distribution. Typically, these are templates, so you have to tell it what's the type that you want to get back. Do you want integers? Do you want a float? Do you want a double? What do you want? They are distributions that give you bools. Okay? And then what are the constructor arguments? Well, it depends on your choice of distribution. Here are two examples. Uniform int distribution is one of the ones that beginners typically need if you want to roll a die or shuffle cards or something. So this example says, I want variates of type long, and I want them in the range low to high, inclusive, low through high. Okay? So if you're rolling a die, that'd be 1 and 6. If you want the normal distribution, the bell-shaped curve, again, you tell it what type you want as a result, but it's parameterized according to a mean and standard deviation, very different from low and high. So how you instantiate this depends on what you choose, okay? So here's sort of the canonical example. It's very simple, and once you've seen this and understand it, you know at least 90% of what you need to know to make use of this header. So the idea is you roll a fair die. Of course, you include the header. I'm not going to bother doing that ever again. You need to instantiate an engine and a distribution. And there's something called a default random engine. I'll say more about that shortly. And then the uniform int distribution, as I showed you above. I made them static for simplicity here. Of course, you get to control their lifetimes however you want. If you want, you can do shared pointers, and you can pass around shared pointers if you want. That's entirely up to you. I'll give you some tips about management in a little bit. And then what you do is you call D of E. And again, as I said, all you're doing with the engine is handing it over to somebody else, in this case, the distribution. And for 90% of the use cases that I've seen in the last 15 or 20 years, this is what you want to do. This is necessary, and typically it's sufficient. Now, one of the nice things is that once you package a distribution and an engine, perhaps like this, you get to do other kind of neat things. And just to give you a hint, suppose I make a native array of size 1,000. I'd like to fill it with 1,000 rolls of a fair die. Okay, std_generate will do that for you. Fill the array A from 0 up to n, and each time it calls roll a fair die, which is a kind of function object. Well, it's a function, but that a function is a function object, and it takes no arguments, so you can pass it off to std_generate. And now you have 1,000 rolls of a fair die. Okay? Just a little taste of some things that you can do. Now, let's explore a little bit in more depth. There are 10 pre-configured engine types that you can choose from. I'm going to pick first on the default random engine. It is special in a couple of ways. It is intended, and you can read the quote yourself, casual, inexpert, or lightweight use. You don't know what algorithm it uses. It's deliberately specified that way. Your vendor gets to choose the algorithm. As a result, the output of an engine of this type is not portable across platforms because different vendors can make different choices. I know there are vendors who say, I want this to be fast. Other vendors say, I want this to be high quality, etc. Okay? But for the other 9, they are nailed down. And you are guaranteed bit for bit portability across platforms. It's a requirement. Your vendor has to do this if he's going to conform to the standard. Now, I've named them for you here. Don't feel you have to memorize them. I'm also not, going to give you a tutorial in, what are the algorithms, because there are lots of places where you can look that up. If you're curious about the names, we did not invent these names. They come from the standard literature, except Knuth B, which I had to invent because I didn't know how else to say this is Knuth's algorithm B from his book. Okay? I mean, I think that's kind of an obvious thing. But all the rest come from various places in the literature. Okay? And some are 64-bit, some are 32-bit, et cetera, et cetera. So why did we pick those 9 algorithms? Because we didn't want to innovate. And those 9 algorithms are extremely well known. They have reasonable quality. They have widely different characteristics. Linear congruential algorithms, for example, are typically very small and very fast, but they don't give you the greatest quality of randomness. On the other hand, if you want quality, Mersenne twistor is what you want. It comes in both 32 and 64-bit variations. But the price you pay is it's not nearly as fast, and perhaps in some applications, more importantly, it's 600 times bigger. Okay, it has a lot of state. That's how it gets the quality. So there are trade-offs to be made. Novices generally don't care, so they just use the default random engine. But once you get into more sophisticated applications, you may very well care a great deal. I'm going to collect questions at the end if you don't mind, because otherwise I'm going to run out of time, I'm afraid. Now, you should know that these engines are actually aliases for templates that are also in the header. Hardly anybody should muck around with those templates unless you're an expert. Because it turns out, I mean, you can tune these templates as much as you like. They all have knobs, typically template parameters. But very few combinations, comparatively, give you anything approaching decent quality by way of output. Coming up with a new engine is hard work. And computer scientists are typically not the best people to do that. What you want are mathematicians and statisticians and so forth. Okay? It's different training that goes into that. So it's okay to know that these are there, but I doubt that many of us in the room or listening to this on video later really are interested in those templates. But you should know that they're there. I told you that engines can actually do more. Here are some of the additional things that an engine could do. Some of these are more useful than others. Engines are streamable in case you want to interrupt the calculation and then restore and come back and pick it up where you left off. That's useful. Reproducibility, as I said earlier, is very important in certain applications. Let's do it again. So you may need to store and then restart. Engines can be compared if they're of the same type. 2 engines compare equal if they're going to give you the same outputs from that point forward. And of course, you can therefore compare for inequality as well. Engines can be initialized, and the correct term is seeded, in more ways than I'm going to show you during this talk. Some are better than others. Engines have member functions named discard, because some people really want to, well, the most common thing people want to do is, I've initialized this, but yeah, I really want it to run through the first 1,000 or first million before I start to use the results. So just throw away the first 1,000 that you generate. You do that by calling discard. Some engines can do this far more efficiently than others. That's why the member function is there. It does it in the manner best suited to the engine. It turns out that distributions don't need any of those extras. And so we actually, in the standard, have a two-tier approach. I've only told you about engines. That's actually the second tier. If you bundle up the requirements that a distribution imposes, what you have is something that we now refer to as a URBG. We changed the nomenclature very slightly for C++17. A uniform random bit generator. It's the only thing you should ever use one of these things for, is as a source of uniformly distributed random bits. And as I say, take it, pass it around to some consumer of those bits, and then you use the result of what that entity gives you. Now, if you have a URBG that also has all these other extra capabilities, such as streaming and so forth, the nomenclature now is engine. So engine is a strict superset of URBG. Okay? It's important to know the distinction because there is something in the standard that is a URBG and not also an engine. Okay? It's called random device. And what it is designed to be is a standard interface to something that is not standard. If you have access to an environmental, sometimes called a physical, source of randomness, for example, dev-random or dev-urandom, depending on whether you care about blocking, or if you have access to a device, for example, that samples atmospheric noise and can transform that into zeros and ones for you. This is a standard interface to such things. Now, by its nature, we can't supply much of the body of this. It's an interface in particular. And the way you use it is implementation defined. Your implementation has to specify how you gain access to it. And what we've said is there's a constructor that takes a string. I mean, you may have multiple sources of randomness, right? So user-defined string, implementation-defined string lets you choose among them, for example, dev-random versus dev-urandom. You may have access to both, et cetera, et cetera. Okay? Interestingly, there is also a member function here named entropy, designed to give you an estimate of, well, guess what? The entropy of your device. So if you haven't seen it before, that's the definition of entropy. There's actually somebody in Europe whose headstone on his grave has a version of this formula. You can find it in the slides if you download them. But please understand, if you call on this function, you're getting an estimate, because sometimes getting it exactly right is incredibly hard to do, depending on your source of entropy, okay? Which means, effectively, it is possible that when you call this function, you're being lied to. So don't rely on it too heavily. There are some vendors who supply this, and you call entropy, and you're always going to get 0. Okay, so don't take it too seriously. But you can ask your vendor to do better. It is interesting as a historical note that way back in 1951, according to Don Knuth, there was a machine called the Ferranti Mark I that had a built-in instruction that gave you 20 random bits into its accumulator using a circuit called a resistance noise generator, and that feature had been requested by Alan Turing himself. I just thought that was an interesting historical note. In case you haven't looked into this, I'm just letting you know, I'm not shilling for anybody here, but there are commercial sources of such devices, and they're relatively inexpensive these days. They come with various kinds of interfaces, USB interfaces, or it looks like a stick, PCI boards, et cetera, and recent CPUs support hardware instructions to do random-related things. There are also some online services that are free. I haven't done this, but based on what I've looked at, which was just a couple months ago, it should be fairly straightforward to put together an interface that will grab numbers online. And if that's good enough for what you need, please feel free. But one word of caution, be careful about your online service, okay? I wouldn't rely on psychic services for random numbers, okay? But they'll happily give you numbers. Okay. I've told you about all the engines in the standard library. Let me tell you a little bit about the distributions. There are 20 of them. We categorize them in 5 families. 2 of them are the uniform distributions, one for int, one for floating point, known as real. 4 of them are classified as Bernoulli distributions. 5 of them are Poisson distributions. 6 of them are normal distributions. 3 of them we classify as sampling distributions. Again, this is not a tutorial in what the differences are among them. This is something you need to know for your application. If you don't, go find a statistician. Okay? It's a fair question to ask why these and not others. And by others, I mean there are hundreds of others, maybe thousands. I haven't done a count. They really are. So we wrote a paper. I think the author was actually one of my then colleagues, but I contributed heavily to it way back in 2004. Things have changed a little bit since then. This was long before C++11, but the fundamental rationale is in that paper. If you're interested, please do feel free to have a look at that. Now, I've already told you that the standard distributions, by and large, with one exception, are class templates. And the template parameter is the type that you want when you call upon the distribution. Some distributions are integer types only. Most of the rest are floating point types only. And one, the Bernoulli distribution, is bool only, and it's not a template, therefore. There's no choice. You're going to get a bool. Okay? I told you a little bit ago that the standard engines are bit-for-bit portable, with the one exception. That is not true for distributions. We do not specify the algorithm by which a distribution gives you a variate. Your vendor gets to choose. And there are lots of choices that can be made. There are literally not just dozens, but hundreds of algorithms for almost any possible distributions. Of course, the better known distributions have more options. And if you look into this, don't just look up a particular algorithm, go to that journal and make sure there aren't corrections in later issues. Please do that. If you're going to implement your own distribution based on an article, make sure it hasn't been corrected. You would be astonished at how many times corrections to ostensibly correct algorithms have been published in the literature. Okay? But the reason we didn't nail it down is we wanted to give implementers the freedom to make these kinds of choices based on what they know of their target platforms. Okay? I would like to stress in particular that one of the very, very strong features of the facilities in this header is interoperability and extensibility. Just within the header, any engine type that you choose to use will work with any distribution type you choose to use. And if you or a colleague or some other source provides more, whether it's engines or distributions, if you adhere to the published interface in the standard, the requirements, so to speak, it's going to work. And we have evidence that this, in fact, happens. You are allowed to provide your own URBGs or engines if you want to go to the extra trouble, your own distributions, and it will seamlessly interoperate. If you write your own engine, you can use it with a standard distribution. You write your own distribution, you can use it with a standard engine of your choice. Or if you write both, they should just work. And we have, as I say, we have evidence of this. In particular, I'll point at two moderately recent developments. There's a new engine called PCG by Melissa O'Neill, fairly recent. There's another one that's just a little bit older, Random 123 by John Salmon and his colleagues. You're welcome to look those up. We're thinking about putting them in the standard someday, but they haven't been around long enough to build up a body of trust, so to speak. So if it goes in the standard, in some sense, we're recommending it. We're just not ready to do that yet. We have reason to believe that these are good quality, but we're just not sure. Just haven't had enough experience with them. And then if you're a GCC user, as I am, you may already know that GCC ships with about a dozen additional distributions that one or more people have contributed. Last time I looked, this is what I found. There might be more by now, for all I know. And they just it just works. Okay, so if you have a need for one of these, GCC will let you have it. I can't speak for any other vendor, but it should work. If you are one of the few people in the world who actually is interested in writing your own distribution, as I say, there's one tool in the header that you might want to use. It's named Generate Canonical. It takes a URBG and calls that as often as necessary to get as many bits, right? It's a source of randomness. So get as many bits as it needs, and then maps those bits as uniformly as possible to the real type range of your choice. All right? And of course, here it's half open. 0 is included, 1 is excluded, and there are very good reasons for that. I keep getting asked for that. Why are integers inclusive and reals are half open? There are very good reasons for those decisions. We can talk about that some other time if you would like. It is described in the standard as it is often a useful step in the process of transforming a value from a URBG into a value that a distribution can deliver to the client. In other words, getting a variate. Okay? All right. So I promised to share with you the anti-pattern, right? Code from hell, as we informally refer to it. Please don't do what I'm going to show you. What's important is not the fact that it's bad code, even though it looks innocuous. What's important is that, as professionals, you know this, but I'm going to give you sort of an extreme example. You don't know where your code is going to end up in 1 year, 5 years, 10 years, 20 years. You may write code today, and in 15 years, it may end up as part of a code base that runs an X-ray machine, delivering treatment to a patient. Get it right. You don't know where copy and paste will end up with your code. We'll send your code. I wrote a library in 1998, 1999. 2 years later, I got an email from a national laboratory saying, "We found your library. We really liked it. We're going to put it on the rocket to Mars." I did not write my library to run on Mars, but I'm told it is. Trust me, you never know where your code is going to end up. Okay? I'm sorry? Are you more proud or afraid of that? I got it right. Okay? I'm serious. Get it right. The key here is when you deal with random numbers, you have to avoid bias. And that's not a vocabulary term in the usual undergraduate computing curriculums. Okay? As usual, XKCD gets the last word. An random generator. There's no such thing as getting the software almost right. Okay? So let's look at the bad code. Don't do this. I'm just going to do it very simply. We're going to mimic the roll of a fair die. Call your engine, whatever number it gives you. Take the remainder after dividing by 6. That's going to be in the range 0 through 5, so add 1. Now you get 1 through 6. Wonderful way to roll a die, right? No. This is wrong. This is wrong. It is so innocuous. How could it possibly be wrong? And yet, it's horrible. You don't have to believe me. I'm going to give you other quotations. So it turns out there are actually two things wrong with it. I'll classify the first as relatively minor, potentially serious, but typically not. And the second one is major. Okay? So what's the minor issue? The minor issue is that there's an assumption in this code, and you don't know if it's true or not. What's the assumption? The assumption is that your engine gives you at least enough bits. If your engine gives you 1 bit per call, you're never going to roll other than 1 or 2, are you? You think that's fair? If your engine gives you 2 bits, you'll never roll a 5 or a 6. Now, I grant you that's unlikely. That's why I call this a minor problem. But, you may not control the engine. Somebody may be handing you an engine. So, you're making an assumption. So at least document it. Okay. Here's the major issue. Typically, n is an integer. And therefore, when you call the engine, you can get any one of 2 to the nth different results. There is no value of 2 to the nth that's evenly divisible by 6. I'm sorry, 3 is not a factor of 2 to the nth. Right? I mean, I think you've known this for a long time, right? I sure hope so. Now, one of our good friends and colleagues has said it somewhat more strongly than I have, so I'm going to quote. First thing he says, this is really awful. And then he went ahead and found a similar piece of code that I don't want to reproduce today, but obviously someone had recognized the issue and said, oh, but I can program around this. Let me use floating point. Heaven help us, which our colleague says is hilariously non-uniform. Love that phrase. Hilariously non-uniform. And then he goes ahead and he explains it in his inimitable style. It's the pigeonhole principle. If you've got 2 to the 32nd pigeons, you can't distribute them into 6 pigeonholes without putting some more pigeons in one hole than others. And of course, this is our friend STL, who's here at this conference, Stefan Laboway. So, don't do this. One of the problems, though, is that it seems to work. Remember one of the early things I said? It's hard to recognize when you do or don't have randomness. Right? If somebody does this, and it's been done thousands of times in the last 50 years, they're going to be rewarded with something that looks random, and they're going to be incredibly excited that their clever solution really worked. But it doesn't work. When you force the range, it eliminates any chance of having a uniform distribution. This is unfair. And the technical word for that is biased. If you have a bias of any sort, you are being unfair, right? And to be correct, you have to work with the distribution and not destroy it. Which means you have to understand what uniformity means and respect it. Now, are we going to get a concept that describes that? I don't know. We'll find out. So my plea to you who are listening today and in the future, let's avoid bigotry in programming, please. Okay? So, how do you do it right? Okay? Let's be virtuous. So let me just sneak up on this by example. Suppose I want a variate, an integer variate in the range 1 through 5. At home, what would I do? I'd grab a fair die, and I'd roll it, and take whatever it gives me, unless it happens to give me a 6, in which case I roll again, right? Until I don't get a 6. And that's, there's the code. Now, I'm not aware of many curricula that teach categories of algorithms called rejection algorithms. But it is a classification for algorithms, right? Where you do the work, see if you like the answer, and if not, reject it and do it again. Okay? So let's take this and just slightly tweak it. Suppose I don't know that it's going to be 1 to 5. Let's say I've got some lower and some upper bound, low and high. Then here's sort of the obvious, I've labeled it naive way to do rejection. Call the engine, which you already know is the wrong thing to do, but call the engine. And if what you get isn't within the range you wanted, reject and go back and do it again, right? Oh, there's so many things wrong with this. I'm just going to give you a small, tiny sample of the things you haven't thought about, that we haven't thought about yet. You may have. What if your engine doesn't give you all the numbers in low through high? What if it gives you some of them, but not all? What if it gives you none of them? You have an infinite loop. You're going to reject forever. You're never going to get something you like. And what about the performance? All right. What if E gives you numbers from a very, very large range, much larger than the one you care about? You're going to spend most of your time rejecting. Okay? Etc., etc., etc. You get the idea. And in the final analysis, when you go through this exercise, you're reinventing, by the time you're done, if you do it right, you're reinventing the standard's uniform int distribution, which of course is already part of the header. So there's no need to do this exercise except for academic reasons, perhaps. I mean, if you're interested in the algorithms, fine. Okay? But not for production purposes. Okay? I mean, there's a certain level of arrogance in our profession. You find the same sort of thing in lots of professions, like surgeons, for example. You have to be sort of ultimately confident in your abilities to get the job done. But a good surgeon knows when not to cut. A good programmer should know when not to code. If you don't have the expertise, either get it or say no. It's the professional thing to do. Okay? So, if you want a random variate, typically what you're going to do is instantiate an engine and a distribution. You get to choose which. You get to pick the parameters of the distribution, both the template argument and the constructor argument. And then for each variate that you want, you call the distribution object and you pass it the engine object so that the distribution can use that engine as a source of randomness. And the canonical example is, declare autovariate equals d of e. Okay? And it's really that simple. And for an incredibly large number of applications, it suffices to have one engine and one distribution. Okay? Why do you need the distribution? For the last time. Because it makes no sense to ask for a random number without context. You have to specify random according to what distribution? People who don't know better think that all distributions are uniform, and it just isn't so. Uniform distributions are incredibly useful, but there are lots and lots of others. So my suggestion, if you get any kind of complexity at all, start thinking about engines and distributions as resources. We know how to do resource management. We do memory management, we do file management, we do mutex management. We treat them all as resources. RAII, for example, is the way to go in many cases, right? If you get into anything that is at all sophisticated, treat these objects as resources and do it the same way. You may need to take explicit control over lifetime, okay? But if your application is fairly straightforward, you can often combine the engine with the distribution. And you've got lots of tools at your disposal to do that. Here are some of your choices. Pair, tuple. You can write your own class. You can write your own class template. You can use bind. You can write a lambda. You can write your own function. You can write your own function template. There are lots and lots of ways to do this. We didn't put any of them in the library because we can't make that choice for you. There is no one size fits all. There isn't even a one size fits many that we were able to converge on. You do need to keep in mind that engine objects are stateful and mutable. So if you're going to pass them around to other code, do not pass by const reference, because they will be impotent when they get there. Okay? They're not const. If you're using concurrent code, you need to serialize. Or you can consider multiple engines, one per thread, for example. It is less well known, but the same is true for distributions. Distributions can be stateful. They don't have to be, and many aren't, but they may be. As one example, there's a fairly well-known algorithm called Box-Mueller, named for the people who came up with it. It gives you normally distributed variants, except it generates them two at a time. Gives you one, caches the other one. Call it the second time, it gives you the one it cached. So it's stateful. Okay? And you don't know whether your distribution uses it. I mean, I don't know, so you don't know. You need to know that an engine's state is influenced by providing a starting value that we refer to as a seed. If you put in a fixed seed, you're guaranteeing reproducibility. The engine size is a factor. It is really hard to initialize Mersenne twister with a single integer. There's something in the library called seed sequence, seedseq, that takes an integer and tries to make more entropy out of it. It doesn't do it particularly well. It's probably best avoided. Feel free to experiment with it. There are better things on the horizon. You have to know whether your application does or does not care about reproducibility. For some applications, it's critically important. It's fatal for others. If you have a game, I think your players will be disappointed if it plays the same game again and again and again, right? It is common to take the current time or the process ID. These are considered low-quality seed data. One of the problems with time is if you need to seed a lot of things, you don't know the resolution of your clock in all cases. You may think you're getting nanosecond resolution and you're getting 1 second resolution. This is bad. Okay. Let me tell you quickly some of the other things you can do with random. We have a new algorithm in C++ 17 known as sample. There's the declaration. It is actually, under the cover, it's two different algorithms, and it picks the right one based on what kind of iterators you give it. Okay? So if you have what the statisticians call a population, you can just think of it as a range, begin and end. You give it that range, it's going to draw from that population. You tell it where to put the copy of what the sample is, how big the sample size you want, and it just does it. Okay? And we're in the process of proposing an in-place sample, which will do partitioning rather than copying. I want to sample these things, just partition it, put the sample at the beginning and the stuff I'm not using at the end. Okay? So that's sort of in process. We can shuffle. Now, I don't have time to go through all of this code, but when you look at it later, what you'll notice is that I am mimicking creating a deck of cards, shuffling it, then displaying it, all with standard facilities. You should know that the original Stepanov's STL had an algorithm called random shuffle that was deprecated in C++14. It is gone in C++17. So best avoided in favor of shuffle. Shuffle was designed to interoperate with the random header. Random shuffle predated it. It is not well known, but the parameters to a distribution can vary per call. Here's an example of how to do it. And in fact, this is an implementation of the shuffle algorithm in the standard library. Again, I'm not going to go through it in detail. But it is interesting to note that in the call to the distribution, which is near the bottom of the screen, where it says D of G comma stuff, you don't have to instantiate a new distribution just because you want to change the parameters of the distribution for this one call. Shuffle, it turns out, needs to change the parameters every time it calls. And we do it all with one distribution. And just some things to think about for the future. You could write an iterator interface to the facilities in the random header. Suppose you had one for a second. What could you do with it? Okay? Here's something tentatively known as variate iterator. And you hand it the generator of your choice and the distribution of your choice. And if I had that, then I can populate a vector by calling copy or copyn. A whole bunch of variates in one call. Or I have a friend who's an engineer, and he said, you know, I really need to do a dot product, and I need to do a dot product with a random vector. Okay, there it is, you're done. If you have an iterator interface. Or an engineer friend of mine, he says, well, you know, I want to simulate noise. So I want to, you know, adjust my values with some random values. Okay, done. One line of code. Okay? If you're interested, I encourage you, again, download the slides and look at this more carefully. And this is what such an iterator interface could look like. So this is the first page of 2. This is basically declarations. There's some design issues you have to figure out. I've just said, you know, non-owning distribution and URBG, but you can put in shared putter or something like that if you want to take ownership in part. And that's it. This is all you have to produce, right? And I know somebody's going to ask, you know, why am I inheriting from iterator, which is now deprecated? That's because I wrote this a year or 2 ago, okay? So, a couple of very fast closing thoughts. Please be wary of resources that you find in random places, okay? The original spec of random was part of Technical Report 1, which was dated 2007. Why did we do that? Because we wanted feedback from a wider community of users, and boy, did we get it. And what we ended up with in C++11 is much improved over the original, sometimes in subtle ways, okay? A couple of things just vanished outright, and a couple of new things appeared. So forget about the original interface. Don't even go there. The problem is the early adopters started offering advice. So before you rely on it, please check the source. I have seen published accounts of the history of random flat out wrong. Just flat out wrong. People think that this originated with Boost. Wrong. It originated with me and my colleagues, and Boost random header, which was written by Jens Maurer. He hardly ever gets credit for it. Did a beautiful job. He actually came to our institution and spent a week with us learning our design before he went off and he produced the boost random header. So that was really the proof of concept, okay? I found all kinds of programming advice, written by people who understand neither randomness nor the header, but don't know what they don't know. Be careful. So I urge you, look at the sources carefully, look at the dates carefully before you rely on what you read. There's good stuff. There's also a ton of bad stuff out there. Here are some places that you may want to look. Random.org I've mentioned before. There's a recent proposal by Moritz Klammler that we are looking at in committee to enhance and simplify the seeding of random engines. It's in the process. Melissa O'Neill has a website and has co-authored a proposal based on what she did there. She's a mathematician, statistician, seems to know her stuff really well. I've been in touch with all these people. The news is that there is a very good chance that in the reasonably near future, once we're done with C++17, we will start working on a new technical specification for an improved random facility for a future standard library. So in closing, again quoting our friends, explicitly quoting Andre, if I were a random number, I'd think I died and went to heaven. All right. Thank you all very much. Thank you very much. Thank you. Do we have time for questions? We have 5 more minutes? I'm willing if you're willing. I'm sorry, I didn't see who was first. Let me just go around the room. Sir.
You said that the processor ID and the time are not good seeds.
Process ID.
Process ID.
Yeah, right.
What do you recommend?
I'm not in the position to make a recommendation for you. Go to Melissa O'Neill's website. She has written extensively about this, so she has some code there. Take a look at that as a source of inspiration. Okay. I'll take one more question, but I'm told our session is officially over. Sorry about that. Sir.
One comment that, so I did random device entropy, it went 0 on my machine, which is 6.1. So my question was that if I'm using the random numbers and I want to use it in a unit test, what are your recommendations on how I can mock up the interface for random?
Oh, that would take much longer than we have time for here. I'm sorry. Okay, let's talk privately some other time, okay? All right, thanks. Thanks again, people.